Hello and welcome to the chapter 14.1 lecture on vector-valued functions. So recall that we learned the vector equation of a line. Its output was a vector depending upon a parameter t. So depending upon the parameter t, it outputted different vectors, and we just thought of those different vectors as pointing to different positions on the line. A vector function is a generalization of that, in which instead of just outputting a line, it could output any curve in 3D space. So a vector value function of one variable is a function whose input is a real number and whose output is a vector. So here's a generic curve in 3D space, which we can think of, or which corresponds to some vector valued function. Depending upon the input t, the vectors will point to different positions on this curve. So let me emphasize that technically a vector valued function, just like the equation of a line, which is the type of vector valued function, outputs a vector, not a point on the line. However, we can think of those vectors that it outputs as pointing to different positions on the line or curve. And we can also have vector valued functions in 2 dimensions. So for example, consider this vector valued function, r of t is cosine ti plus sine tj. First, recall that sine squared plus cosine squared is 1 by the Pythagorean theorem. And we can think of these different vector outputs. Well, they have an I and j coordinate, and the I coordinate, this adjacent, is going to be cosine of t. The angle, if we think of the parameter t as the angle, and the opposite side is going to be sine of t, which is the j coordinate. So it always lies on the unit circle, and as t varies, again thinking of t as the angle, then we move around this unit circle, and it parameterizes the unit circle. And we can extend this type of vector value function to 3 dimensions in various ways. So here's the vector value function that we just found. This is a circle on the xy plane. And one way to visualize vector valued functions is similar to what we did in 13.6 with traces. So looking at this, we can think, okay, what does it look like on the xy plane? Well, it looks like a circle on which we're moving around counterclockwise. So this blue circle here. And then what does z do as we move around? Well, sine oscillates up and down. So as we move around, we oscillate up and down, always with our xy trace being on this circle. So everywhere the function is above the perimeter of this circle. So that goes up and down like this. Okay, and again, technically, each of these outputs is a vector. So the technical output would be, for example, this green vector, but it points to different positions on this curve. Vector valued functions, just as ordinary functions, can have domains. And the domain of a vector valued function, by default, without any domain given, is the largest set on which all of its coordinate components are defined. Just as with ordinary functions. And this is equivalent to the intersections of the domains of the various components. After all of them must be defined. And we can also restrict the domain of a vector-valued function manually if we wish to produce a curved segment, such as illustrated at right. So here it looks like we're specifying that t must vary between a and b. So that would mean the domain of this would be a to b. So let's do an example. Let's find the domain of this vector-valued function. So no domain is specified here, and that means that by default, it is going to be the largest set on which all of these coordinates are defined. You can see that some of these coordinates are not defined for some t, actually all of them, like 1 over t, that's not defined when t is 0. So automatically from this part, we know that 0 cannot be in the domain. So let's consider all three parts. So the first part, root 4 minus t squared, the domain of that is -2 to 2 inclusive, else we take a square root of a negative number. If t is bigger than 2, then t squared is bigger than 4, and we have 4 minus something bigger than 4 is negative. And likewise, in the negative direction, -2 squared is 4. Anything less than -2 will make that negative. Okay, so our domain must be at most this, but then we must also exclude some other values, such as 0 from the 1 over t part. So from the 1 over t part, the domain of that is everything except 0. And from the 1 over 4 minus t squared part, that means that 4 minus t squared cannot be equal to 0, else we're dividing by 0. And that means that t cannot be equal to plus or minus 2. So therefore, in total, it must be between -2 and 2 inclusive, but not equal to plus or minus 2. So it's like -2 to 2, but also excluding t equals 0. So that's -2 to 0, non-inclusive, union 0 to 2, non-inclusive, is the domain of this vector-valued function. And vector-valued functions present an intrinsic orientation to curves. So here's an unparameterized curve. The tangent vector is in one of either two directions. It's unoriented, while a vector-valued function that gives an intrinsic parameterization, namely as t increases, has an intrinsic direction to it. And that intrinsic direction given by the movement on the curve as t increases gives a single tangent vector, well, up to scalar multiplication, in a particular direction tangent to that curve. So in this example, for example, that we did, the orientation is indicated by these arrows, indicating that as t increases, we're moving this way along the curve. Okay, let's consider this vector-valued function. And let's try to visualize what it looks like. So similar to how we can understand and visualize quadratic surfaces through their traces, to visualize vector-valued functions, we often want to first visualize their projections onto one of the planes. typically the xy plane. And then we can kind of add the z component in and see how it moves up and down depending upon, well, what t is in the z direction above the projection onto the xy plane. So the xy part here is this, and that's the vector function we already encountered. It's going to be a circle on the xy plane with a counterclockwise orientation. Okay, so now the z component will do some movement above the circle. Let's think about what that might look like. Well, as t increases, t over 2 pi is going to be increasing. So the projection on the xy plane winds around in a perpetual circle with period 2 pi. And the z coordinate increases by 1 for every unit of rotation. When t is 2 pi, then the z coordinate is 2 pi over 2 pi is 1. And likewise, when it's 4 pi, then it's 4 pi over 2 pi is 2, and so on. So every time we wind around, we're now 1 unit higher than we were in the z direction. So what does that look like? Well, it'll be what we call a helix. Note that this curve has a 4 by the cosine, but it captures the idea. So ours is a perfect circle, not this ellipse thing. So imagine that this is a circle. We wind up 1 unit when we go around once, go around twice, we wind up a 2nd unit, and so on. So in total, we'll have this winding helix shape, a growing spiral. With this intrinsic counterclockwise orientation given by the motion of direction as t increases. So let's consider this vector valued function. That is the actual one that was just graphed, but imagine that we're considering it from scratch. How could we find it? So the only difference here is this 4 by the cosine. So first we might want to find the projection of this onto the xy plane, namely this. Let's plug in some points and plot. So when t is 0, then our coordinate is 4, 0, plugging in t equals 0 into this. Okay, there's 4, 0. When t is pi over 2, then our coordinate is going to be 0, 1, plugging in pi over 2. When t is pi, then our coordinate is -4, 0. And similarly, when t is 3 pi over 2, then we're at 0, -1. So it looks like we'll have this elliptical shape. And then when we get to t over 2, t equals 2 pi, then due to the periodicity, we are back where we started, and we're winding around in this elliptical shape. We'll show in a bit how to find that it's an actual ellipse. Okay, so here's just a better picture of that. And once again, the z coordinate, t over 2 pi, increases by 1 every revolution of 2 pi. And the result is this elliptical spiral. with the projection onto the xy plane being that ellipse that we just found. Okay, so just plotting points, we found that this looks like an ellipse. How can we actually prove that it's an ellipse and find the standard Cartesian equation for that ellipse? Okay, so we want to eliminate t to get a relational equation. And by relational equation, we mean an equation on the Cartesian plane. So what we mean by this is that we only have x and y in it. Okay, well, for cosine t, the coefficient of I is x by definition. That is the x coordinate of the vector. And sine t, that is y by definition. Okay, so we know that x is equal to 4 cosine t, and we know that y is equal to sine t. And we want to eliminate t from this system. So maybe you're thinking, okay, well, you can do a substitution, solve for t in, say, the second equation, t is arc sine of y, and then substitute that into the first equation, and we have that x is 4 cosine of arc sine of y. Okay, that does mostly work. We have an issue with the domain restriction of the arc sine, and then it's kind of annoying to find cosine of arc sine of y, but it would mostly work. But there is a much easier way to do it, and that is to utilize trigonometric identities. So in particular, we know that sine squared plus cosine squared is 1. So if we can get a relation like this, then t is eliminated. The right-hand side has only a 1 in it. So maybe what we can do is something like square both sides of both of these, then we'll have the sine squared and cosine squared, and add them together in some way so as to eliminate the t in one fell swoop. However, we can't just square both equations and add them together because we have that 4 there. We would wind up with a 16 cosine squared and a 1 times sine squared. That's not what we want. We want them to have the same coefficients. So maybe what we can do is multiply both sides of equation 2 by 4. So that now both of these have a 4 coefficient. And then when we square them, they'll have the same coefficient. And we can apply this identity. So let's consider not sine t, but 4 sine t. And 4 sine t, this is 4y, multiplying both sides of that by 4. And we want to square that and add it to our 4 cosine t. And that 4 cosine t is x. And we want to square that. So this guy is 4y squared. And this guy, so here that 4, that was already part of x, so that is just x squared. Okay, but we still need that right-hand side. What is this equal to? Okay, well, now that they have the same coefficients, we can utilize the Pythagorean trig identity. So this is the same as 16 sine squared t plus 16 cosine squared t. And that is factoring out the 16 sine squared t plus cosine squared t. And sine squared plus cosine squared equals 1. So that's the same as 16. So therefore, 4y squared plus x squared is equal to 16. Since that guy was 4y, that was x, and the right-hand side is 16. So that means that 16y squared plus x squared is 16. And dividing both sides by 16, that means that y squared plus x squared over 16 is 1. And writing that in our more standard form of an ellipse, that is x squared over 4 squared plus y squared over 1 squared is 1. And that, as you'll recall from our review of ellipses, is an ellipse with x radius 4 and y radius 1. And that is exactly what we got before from plotting it. Except now that we've proved that it is indeed that ellipse. So that is the method for converting vector functions to relational Cartesian equations. Eliminating t. We just found that this is x squared over 4 squared plus y squared over 1 squared is 1. That 4 is this, and that 1 is that. So you try your hand. Try to find the relational Cartesian equation that this vector function traces out on the xy plane. I encourage you to pause the video and again try to utilize a trigonometric identity like sine squared plus cosine squared is 1. Okay, so we have that x is cosine t, y is sine squared t. Once again, we're thinking, okay, we know that sine squared t plus cosine squared t is 1. How can we relate x and y so as to get this identity to eliminate t? Well, y is sine squared. That's already taken care of. And x is cosine t. We want a cosine squared. So if we square that cosine, squaring both sides of this, that is x squared. But we know that sine squared plus cosine squared is 1. So therefore, y plus x squared is 1. So this is y is 1 minus x squared. An upside down parabola. But is it that whole parabola? So remember at this point, we sometimes need to be careful of the range. So we know from this that, well, cosine t is always between -1 and 1. So what that means, since x is it, is that x is always between -1 and 1. So this is a domain restriction of x in our relational Cartesian equation. Okay, so it's this with the domain restriction that x is between -1 and 1. Okay, so it was this, and graphing that upside down parabola with x between -1 and 1, it looks like this. And as t increases, well, when t is 0, we begin at 1, 0. So we begin here. That's the point, t equals 0. And as t increases, we're first moving this way and then moving back. So here's a visualization of that. I have graphed the equation y is 1 minus x squared with our domain restriction, and also our original parameterization, cosine t comma sine squared t. And let's see what happens as t increases. See that blue dot? So as t increases in our parameterization, we are bouncing back and forth along that parabola segment. Now, let's think back to, where this is slightly different. Let's think of this vector function. Okay, so once again, the xy trace is a unit circle, our standard parameterization of the unit circle. And now our z above that unit circle, because of the sign, it'll be bouncing up and down. So when x is 0, sine is 0, so we begin here, then sine increases, and then decreases again, increases again, and decreases again above that unit circle. And sometimes we might be interested in in a surface on which a vector function lies. So it looks like this vector function lies on this hyperbolic surface. Let's find the equation for it. So, as usual, we can eliminate t by relating x and y, and also z in this case. And here we'll need this other trigonometric identity. Recall the double angle formula, sine of 2t is 2 sine t cosine t. The reason we'll need this is this sine of 2t right here. So, we know that 0.4 times sine of 2t, well, must be equal to 0.4 times 2 sine t cosine t by that double angle formula. Okay, but this guy is our z. And cosine t is our x, and sine t is our y. Well, we look at that. That is our x, and that is our y. So we immediately find a surface on which it lies. So that is z is equal to 0.4 times 2 is 0.8 times x, y. Is the surface on which it lies. And that's denoted here. This surface here was a hyperbolic paraboloid. It doesn't look like our standard form of a hyperbolic paraboloid because it is at an angle, but it turns out that this is also a hyperbolic paraboloid, as one can do with a change of coordinates, which we won't be doing in this class. Okay, so you try your hand. Let's find the surface on which this lies. Here we have a cosine of 2t, so we need the double angle formula for that. Recall that cosine of 2t is cosine squared minus sine squared. So therefore, we can relate cosine 2t to that sine and that cosine by maybe taking our x here and squaring it. Squaring that, we'll have that sine squared, except we have this 2 by the cosine t. So maybe we'll need to do something like first multiply this by 2. 2x is 2 sine t, and then square it and add it to the square of y. Pause the video if you want to think about that, try to get it. Okay, so what we wanted was a cosine squared minus a sine squared, because we know that that's cosine of 2t. So let's take our y, which is the 2 cosine t, and square that. If we square that, we'll have a 4. So let's stick a 2 here by the sine t. When we square it, we'll have a 4 again. And we want to subtract. So let's subtract 2 times sine t. This guy is now 2 times x. X is sine t, 2x is 2 sine t. Okay, that is 4 cosine squared t minus 4 sine, oops, and we square that as well, minus 4 sine squared t. Which is 4 times cosine squared t minus sine squared t. Okay, but we know from our double angle formula that this is cosine 2t by double angle. But cosine of 2t is z. Right there. So this is therefore 4z. And 2t, so the only way to relate the sine t and cosine t to it was using that double angle identity. So we have found that y squared minus 2 times x squared is equal to, well, 4 times z. So y squared minus 2 times x squared is 4z. So y squared minus 4x squared is 4z. And we can simplify that if we want, but that is the equation of a hyperbolic paraboloid. Oh, and you might be wondering, wait a moment, this is a curve in 3D space, while this is a surface. Well, we only utilized or found one identity between x and y and z. We could find another identity by realizing that x squared, or rather 2x squared plus y squared is 4, utilizing the ordinary Pythagorean trigonometric identity to realize that it lies above an ellipse, and in that way get the actual parameterized equation for it that isn't a vector equation. Okay, so now let's at last begin some actual calculus in this class. So calculus begins with limits. And our definition of the limit of a vector function is the same definition of a limit from calculus 1, except adapted to vectors. So a vector valued function r approaches a limit L as t approaches a, written in our usual notation, if the difference between our vector function and our limit approaches 0 as t approaches a. And note that here, L is itself a vector, since a vector must approach another vector. So because of that, that means that this is really the magnitude of the vector. Specifically, the magnitude of the vector difference. So let's do an example. Let's evaluate this limit. So it turns out that you can always evaluate vector limits by just evaluating the limits of their components, well, component-wise. So the limit as t approaches 0 of sine t over t is 1. Let me remind you of why that is true. We can apply L'Hopital here. L'Hopital says that if a limit is of the form 0 over 0 or infinity over infinity, it's equal to the limit of the quotient of the derivatives. And sine of 0 is 0, and t at 0 is 0. So that's the same as sine t derivative over the derivative of t, which is the limit as t approaches 0 of cosine t over 1, which is the limit as t approaches 0 of well, 1 over 1, which is just 1. And similarly, well, not similarly, the limit as t approaches 0 of 2t, there we can just directly plug in. That's 0, 2 times 0. And the limit as t approaches 0 of tangent of 3t over t is again by L'Hopital. Okay, so derivative of tangent of 3t is 3 secant squared of 3t. Derivative of tangent is secant squared, and by the chain rule, we pull out that 3. Since derivative of 3t is 3 over 1, when we're taking the limit of that. And secant is 1 over cosine, and cosine of 0 is 1. So we have 3 over 1 is 3. So the limits component-wise yield 1, 0, 3. Now, for the sake of illustration of this rigorous definition and why this would always work, let's plug into this and make sure it is equal to 0. Okay, so we're interested in showing that the difference between our vector function and our supposed limit as t approaches 0 is indeed 0. So we take the difference between our vector function and our limit, that is this, subtracting component-wise, and we're interested in the magnitude. Well, the magnitude is the square root of the sum of the squares. So this is 0 squared, that goes away. This guy is necessarily 0, since sine t over t approaches 1, and this guy is necessarily 0 in the limit, since this guy approaches 3. So it yields 0 indeed. And a vector-valued function r is continuous at a point A if its valuation at A is the limit as t approaches A. This is again the same definition of continuity as from Calculus 1, except now with vector functions. Oh yeah, so don't get caught up with these details. Again, for any vector function, you can always evaluate the limit by just taking the limit of the components using ordinary Calculus 1. So for example, we just found that the limit of t as t approaches 0 of this guy is 1, 0, 3. However, this function is not defined at 0. For example, we have a division by 0. So it's not defined at 0. So while it has a limit at 0, it's not continuous there. Okay, so consider this vector-valued function. Let's find some limits associated with it, and then find where it is continuous. I encourage you to pause and find these limits by hand. It'll be a good Calc 1 review. Again, each of these limits, we just find the limits component-wise. Okay, so as t approaches 0, I'm going to say this verbally. So plug in 0, we have 2 over 1 minus 0. No need to do anything there. As t approaches 0, sine t over t approaches 1, just like as before with L'Hopital. And as t approaches 0, e to the negative t is e to the 0 is 1. Again, just plugging in. Okay. As t approaches 1. Okay, then we have 2 over 1 minus 1 squared. That's 2 over 0. That'll necessarily go to infinity. Who cares about the rest now? This is undefined. And as t approaches infinity, okay, now we have 2 over 1 minus infinity squared. That's 2 over an arbitrarily big number. 2 over a huge number goes to 0. So first component is 0. Okay, second component, we have like sine of a huge number over a huge number. Sine is always between -1 and 1, while this denominator goes to infinity. So we have a finite number over an approaching infinity number. So a small number over an enormous number goes to 0. Goes to 0. And e to the negative t. So recall the graph of e to the t, for example, or e to the negative t. Okay, so there's y is e to the negative t. It's the graph of e to the t swapped around the y-axis. So that approaches 0. And let's find all values of t at which r of t is continuous. Okay, well, this is going to be continuous wherever it's defined, since none of these components are piecewise. So its continuity is the same as its domain. Okay, so let's find its domain. The domain is everywhere all three components are defined. So from this part, we know that t cannot be equal to plus or minus 1. Otherwise, we have division by 0. From this part, we know that t cannot be equal to 0. Otherwise, we have division by 0. And from this part, well, t can be anything. There is no restriction there. So we have that t cannot be equal to plus or minus 1, and t cannot be equal to 0, and it is defined and continuous everywhere else. Okay, and we concluded the 13.6 lecture by finding the equation of intersection of two planes. And now we can find the equation of intersection of two curves. So here are two elliptical paraboloids, and they intersect in some curve. You can see that they intersect in this wavy red line. And we're interested in finding the parametric vector equation of that line. So you might be thinking, okay, well, back when we found the intersection of two planes, we wanted a parameter t. So we let one of the axes be that parameter. In that case, we let z be t. So we might be thinking, okay, can we let z be t? Well, if we let z be t, then we would have two outputs for each t. And that would make it not a function. And similarly for the other two axis choices as well. So that method is not a method that will work here. Okay, but think back to earlier in this lecture. This looks like something that we dealt with. And what was the parameterization of that? Well, we parameterized with the projection, or realizing that its projection on the xy plane is a circle, or possibly ellipse. So let's instead think, okay, maybe we should let x be cosine t and y be sine t. Okay, so you might be thinking, wait, how do we know that that's a circle and not an ellipse? That would be a very good thing to think. And I'm going to gloss over that detail for the sake of illustration, and it's not relevant to the homework. However, we could know by actually letting z be t, and then we would get, well, two outputs. It wouldn't be a function. It would end up being a plus or minus square root from a quadratic formula, and we could recognize that it is a circle, and then go back and do this. Again, it won't be relevant to the homework, so I'm going to gloss over that in the interest of time and to not make this, and to illustrate the main point. The homework will usually give you something like this to start with. Not usually, always. Okay, so with that in mind, we'll let x be cosine t and y be sine t. Okay, so that means that now z is, from this first equation, 3 times x squared plus y squared, which is sine of t, plus 1. Okay, that's perfectly fine, but it's not perfectly fine at all. Because this can be simplified. So actually, it is fine, just not perfectly fine. So 3 cosine squared, well, the cosine squared and the sine squared would go away. So maybe we should write this as 2 cosine squared of t plus another cosine squared of t plus sine squared of t plus 1. So this guy is that guy. Okay, and now this guy equals 1. So this is the same as 2 cosine squared t plus 1 is plus 2. So the parameterization should be, well, our x, y, and z coordinates. So that's cosine t, comma sine t, comma 2 cosine squared t plus 2. Okay, but it must lie on both surfaces. So we'll check now with the second equation. In the second equation, we have z is 5 minus cosine squared t minus 3 sine squared t. Okay, so this is what I had in mind when I said this is not really fine. We can't verify that this is the same as this. Not in this form, at least. But if we use this simplification using the trigonometric identities, then we should get the same form here. So let's do our trigonometric identity. We'll do the same trick. That is 5 minus cosine squared t. Okay, minus 2 sine squared t minus another sine t squared. Okay, and minus cosine squared minus sine squared. Those together are minus 1. So we have 4 minus 2 sine squared t. Oh no, have we made a mistake? This does not look like that, does it? Well, it does. Let's transform that sine squared into a cosine squared using the same identity again. Because sine squared plus cosine squared is 1, that means that cosine squared is 1 minus sine squared, or sine squared is 1 minus cosine squared. So from that second equation, we found that z is 4 minus 2 sine squared. And now we're thinking, okay, well, sine squared plus cosine squared is 1. So that means that sine squared is 1 minus cosine squared. Okay, so doing that replacement, we have that. 4 minus 2 is 2, and minus 2 times minus cosine is plus 2 cosine. So we have that same thing again. So either way, this is our output on either surface, and therefore the vector equation of that curve of intersection. So that concludes our 14.1 lecture. Have a great one.